So, but you sort of see where we're going. Now, a lot of this is in the notes, so I'm not going to spend too much time on this. What I'm going to try to do is give you some time to get in groups today to also do some of the work. And a lot of it is very theoretical. I'm afraid that when you sort of ask me for a concrete example, the last thing I tend to think of is something that has actual numbers in it. Okay? Typically, as concrete as I get is, well, there! A concrete vector, x. Okay? So, if I'm not concrete enough for you, then stop me and say, but can you actually give me an actual example? All right? Don't be shy. Okay, so what's going on? Well, you've learned how to measure how big a real number is, right? I have a strange suspicion that this might. Let's put this away. If we have a number x in R, how do I measure how big that number is?
Square
Square root?
You mean
No, just the number.
Oh.
Scalar.
It's absolute value.
Absolute value, right? Okay. If we have a number, well, I shouldn't have said x. That's, of course, what confused you, right? Yes, of course. It should have been alpha. We should have used a lowercase Greek letter. Absolutely. Right? Now, if we have an alpha that is a complex number, how do we measure how big it is?
Alpha times the conjugate.
Okay. Well, you could say it's still the absolute value, right? But what you're saying is that's the same as alpha times its conjugate, which is the same as alpha times its conjugate. Square root. Thank you. Just testing you there. Which is the same as if you write alpha as its real part plus its imaginary part, then it's equal to the real part squared plus the imaginary part squared, the square root of that. Right? So far, so good. Okay, we now have a vector x that is in Rn. How should we measure how big x is? We're going to use the Euclidean norm. So how would the Euclidean norm be defined? Well, first of all, what symbol should we use? Well, we're going to use this double bar thing for norms, okay? And it turns out that Euclidean norm is typically denoted as the 2 norm, for reasons that will become clear in a little bit. And what is it? Well, it's the sum of the squares. And then you take the square root of it. Right? Now, what kind of special properties does the Euclidean length have? 2 norm have? Well, in general,
It's linear. It's a basic triangle inequality. It's always greater than or equal to 0.
If you tilt your head, it's the same.
Huh?
If you tilt your head, it's still the same.
It's preserved by linear transformation. Up to and include
under
linear transformation.
You know too much for this class. Get out.
Sorry.
All right. So let's bring it back. So let's come up with a definition. Okay. The definition that we want is, so let now mu be something. Let's go ahead and do this on the complex vectors. It's a mapping to R. Okay. Then this function is a vector norm. If for all x and y in Cn, be something missing here. And alpha in C, x is not equal to 0 means that the norm of x is greater than 0. And this has the name, this means that the function is positive definite. Positive definite. Okay. The second one is if you take the vector x and you scale it by alpha, then you get back the length of the vector x multiplied by alpha, except you need to take the absolute value of that. Okay. And then you have the triangle inequality that you mentioned, which is that if you add two vectors together, then the result of that is less than or equal to the lengths of the separate vectors. And that's the triangle inequality. And this, by the way, is called homogeneity. So, notice that actually these two together imply that if x is that the norm of x is 0 if and only if you feed in the 0 vector. And that's actually an exercise able to do that. All right, and the Euclidean length has this property, which is a little bit difficult to, well, it has all of these properties, and the triangle inequality actually is a little bit tricky to prove, and to prove it you use a little lemma that's known as the Cauchy-Schwarz inequality. Okay, and all of that is in the notes, so you can just kind of puzzle through that and figure it out. Okay, now, question. Is this cheap to compute? It's cheap enough. Okay? I mean, you can think that anytime you have a vector with n elements, you're going to have to somehow look at all of the elements. So invariably, it's going to take order n time to compute. This takes order n time to compute. Okay, it's good enough. Okay. There was a time that taking the square root, or actually it's still the case, that taking the square root is actually quite a bit more expensive than just a normal operation, like a multiplication or an addition. That's just a matter of making sure that you work with really long vectors so that you can ignore that. All right? So, not bad. Okay, now, it turns out that later on we're going to want to define matrix norms that go with these vector norms. And it turns out that computing the matrix 2 norm that is associated with this vector 2 norm is actually impossible to compute in a finite amount of time in general. And that has to do with it being related to eigenvalues of certain matrices. And there is this little thing in Galois theory that proves that for matrices larger than a 4×4, you can't, for a general matrix, compute the eigenvalues with a finite algorithm, and all hell breaks loose. Okay? Now, the fact is, we don't care about getting the exact answer. We only care about being approximately there, and therefore we can have practical algorithms that approximately give us the 2 norm in a certain amount of time, but even that is very expensive, and therefore the 2 norm is kind of poisonous when it comes to practical implementations. All right? So, there you have it. But great theoretical tool, so we're going to use this. So, to overcome the fact that later on when we look at matrix norms, we want practical algorithms for computing norms, we come up with other norms, other ways of measuring the length of a vector. And one such thing, now I'm just going to go through here and do everything with real numbers, fair enough? In the notes I do it with complex numbers. Why make things more difficult? So there's also something called the 1 norm. Now, you can think of this as this right here. The one norm is the, what do you call it, the one root? The no root? I don't know.
Yes.
Of
Actually.
chi 0 to the first power plus chi 1 to the first power in absolute value. This should be here, this should be here. Get my drift? Now what's a simpler way of saying that? Just take the sum of the absolute values, right? It should have been -1. Boy, I'm not really with it today. Get it? So, this is often called the taxi cab norm. And the reason is that, you know, if you're in New York City and you think of every block to be square, if a taxi needs to take you from point A to point B, the taxi is going to have to follow the streets, and therefore the distance really is how far the taxi needs to go, as opposed to the straight line that a bird could fly. Of course, a bird might have to fly over all those buildings, but let's not go there. Get the point? So, this is known as the one norm. So this now is the two norm, the one norm. The one norm is really cheap to compute, right? The absolute values, cheap. Adding them together, cheap. Good stuff. In general, there is a family of norms called the p-norms, which then, of course, is just a natural extension of this. All right. And then, so these two are now just special cases of p-norms. And by the way, I always get confused. P can be larger than 1 and or smaller than 1. Okay? It can actually be between 0 and 1. Don't include 0. Turns out that rarely is the p-norm useful. But it's a nice way of tying them all together. And then there's something called the infinity norm, which strictly speaking is defined as the limit, limit as p tends to infinity of the p norm. Okay? If we just had one term, what would this be? Just the absolute value of that one term, right? If you let p go to infinity, what happens to all of these numbers?
The biggest number dominates.
The biggest number dominates, and then you take the pth root of the biggest number raised to the pth power, and what do you get back?
Biggest number.
What shall we say? Something like that? It should be chi. Yeah, it is chi. You get the point? Okay, so to compute the infinity norm of a vector, all you have to do is scan through all of the elements and pick out the one that's largest in absolute value, magnitude, and now that is your norm. And notice that you can prove that all of these norms are actually norms. I mean, I'm just calling these norms. What are they really norms? So maybe what you can do is just get together with the person next to you. Well, maybe we should go through one of these. Okay, let's go through one of these together, prove that it's a norm, and then I'll let you do an exercise of the other one. And let's not Let's not do the 2 norm. You can read up on that. Oh, that's fun. Proving that the 1 norm is a norm is an exercise. Okay. Let's do an exercise together and we'll see whether I get it, okay? I haven't done this particular one in a while, but it's good for you to see me struggle, right? That way you can figure out that struggling is okay, as long as in the end you get it. So, let's create some room. So what we'll do is we'll together prove that the 1 norm is a norm. And then what we'll do is we'll take a break where you guys work on in pairs proving that the infinity norm is a norm. All right? That way you get a little bit of practice. So, okay, homework. Homework 2.7 says the vector 1 norm is a norm. Now, what is it that we need to do to prove that something is a norm? Well, what we need to do is prove that these 3 conditions hold. So you simply go through it. And you go. Okay, so let's say let x be not the 0 vector. Show that the 1 norm is greater than 0. Notice that. What do I do when I do this? I go ahead and I write down what it is that I need to prove, that then guides me, and then I get started. So what do we have? The 1 norm of x. Well, you can't do a heck of a lot until you actually write down what it means. So you know that that's equal to, let's actually use the summation. I equals 0 to n minus 1 of the absolute value of chi sub I. Now, where do we go from here?
Prove it for 1 element vectors and maybe use induction to.
Yeah, you can, you can just observe that all of the terms are non-negative.
That's probably, yeah. I mean, you could do it by induction, but simply sort of say, well, what I really would like to do is to say it's greater than or equal to you can sort of say, well, you know, we're summing a whole bunch of them. Let's grab the biggest one and say, well, since we're adding other things to that one, it's going to be greater than or equal to that, right? But if x is not the 0 vector, what do we know about the maximum value in that vector?
Not 0.
There must be at least one element that's not 0, right? So this is strictly greater than 0. Okay? Not the only way. What's the shortest way of actually saying that this is true?
Oh, do we need an n on the second to last line?
End of proof?
Or no, the letter
N?
for n elements.
This one
Yes.
here? Well, I'm trying to indicate that this is the index at which the maximum is attained. So max here stands for an index. So I'm not sure where the n comes in.
Multiply the whole thing by n
Well,
times
that's,
okay.
no, it's less than n times the max, right?
Oh, yes, sorry. Yeah.
Gotta be careful, all right? So, the shortest proof would be to say, da, right? And sometimes that's okay. You could, of course, have said, well, this is obviously true since the elements of x are non, you know, that at least one element is non-zero. I mean, any kind of indication like that is just fine. So then you go and you say, okay, well, what about the second one? again, you got to go back to the definition, right? The definition here is alpha I equals 0 to n minus 1 of the absolute value of chi I because of the definition of scaling of a vector. By the way, notice that in class I often say because of. Ideally, when you write a proof, you give a hint as to why, so that whoever is grading it can see what your logical thought is, okay? And often what you will see is that in the actual proof that I have in the notes, I try to actually give indications of what's going on. Sometimes it gets sloppy. And that's why it's important to also go and read my proofs in the notes, because there's a lot of this unsaid stuff that I'm not putting on the whiteboard. Okay. And then, of course, we know that this is equal to the summation I equals 0 to n minus 1 of alpha times chi I. And why is that? That's algebra, right? And then we can bring the alpha out. And that's then just that right there, right? By the definition of the wonder. These two tend to be very easy to prove. And then we get to that x plus y in one norm must be less than or equal to x plus one norm y. Ooh, I was a little sloppy here. I should have said what it is that I needed to prove and then prove it. Anyway, what do you do? Well, you start with the definition. It's equal to, strictly speaking, you should say, well, that's equal to chi 0 through chi n minus 1 plus psi 0 through psi n minus 1 in one norm, which then is equal to psi 0. Now notice that here I actually did break it down into individual elements. I don't do that very often. Plus psi 0 through chi n minus 1 plus psi n minus 1. You can sort of see where this is going, right? Get it? Okay. Why don't you break up into teams of 2 and do a proof of the same thing but for the infinity norm? Right. Get out a piece of paper. Let's spend 5 minutes on it. So hopefully you've had a little bit of experience with this. You kind of noticed that the maximum comes in a lot, right? So we just kind of manipulate that, and let's just move on. Fair enough? So you can finish this as a homework exercise for next time. I still need to post the homework, by the way. All right, any questions about all of that? Yes?
I didn't quite understand how did you prove the third property?
The third property? Oh, so you'd like to see the dot, dot, dot? Well, that's, that's one of the reasons why getting you to try it yourself is... Right, so let's see, okay? What's the definition here? Well, the definition is the sum from I equals 0 to n minus 1 of the absolute value of chi sub I plus psi sub I, right? That's just the definition. And then from algebra, you remember that this is the same as the sum from I equals, or sorry, it's bounded by this right here. Okay.
But isn't that the triangular equation?
Well, this is the triangle inequality for scalars,
So below.
which you're allowed to use. Okay? Yeah, okay. Yeah, because otherwise you kind of... Right? And then, so your question really is more, what exactly are we allowed to assume? So anything you learned in algebra about scalars, you're allowed to bring to the table here. Fair enough? So that was a great question. So with that, hopefully people can work out the same thing for the infinity.